Hello, is this audible now, Mariam and Afan?
Yes, ma'am.
All right. Now, see, let's do a revision of semiconductors. But before that, we had done differentiation or classification of solids. So, the solids can be classified into three categories: conductor, semiconductor, and insulator. Now, see, in this, you have to remember the order. You have to remember the order of resistivity and the order of conductivity. So the order of resistivity is this. Mainly you have to remember this point and this point. So resistivity of inductors is the highest and the resistivity of conductors is the lowest. And just the reciprocal of this is for conductivity. Conductivity of conductors is the highest, whereas conductivity of the insulators is the lowest. So semiconductors lie in between them. Now see, this was the classification on the basis of resistivity and conductivity. If we have to differentiate it on the basis of energy band theorem. So energy band theorem says that in conductors, the conduction band has partly filled electrons or the valence band has completely filled electrons. Now see what can happen. Either the conduction band and valence band both can overlap or both can be at a certain distance separated, but conduction band would have partly filled electrons, or it can be empty. But in case of valence band, it has to have filled electrons only. So conduction band is partially filled, whereas valence band and conduction band may overlap each other. Now see, in case of insulators and semiconductors, conduction band is totally empty. It's just that valence band is filled. Now electrons do get excited from valence band to the conduction band. Now see, when electrons get from excited from the conduction band to from the valence band to the conduction band, then they have a certain energy gap. When this energy gap crosses, then only one is able to see the electron emission. So conduction band is empty, valence band is filled, and energy gap is greater. So see, in case of semiconductors and insulators, what difference comes is that conduction band is empty in both the cases, valence band is filled in both the cases. The energy gap band difference, this difference is known as energy gap. The difference between conduction band and valence band, this is known as energy gap. So in case of semiconductors, conduction band and valence band have very little energy gap between them. Whereas in case of insulators, there's a large energy gap. Energy gap is greater than 3 electron volt. And in case of semiconductors, it is less than 3 electrons. So you have majorly two major examples of it, silicon and germanium. And you have to remember their energy gap, 1.1 electron volt, 0.72 electron volt. Now see, types of conductor. On the basis of impurity, if we separate the semiconductors, if we have to classify it, they are mainly of two types: intrinsic semiconductors and extrinsic semiconductors. Now see, extrinsic semiconductors are of two types, p type and n type, whereas intrinsic semiconductors are the pure semiconductors. Now see, in case of intrinsic semiconductors, when the temperature increases, thermal energy increases, electrons may get broken. So this is known as intrinsic semiconductor, where there is no presence of impurity. Like you can easily see silicon, 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 all are silicon together connected through holes and electron pair. But in case of extrinsic semiconductor, we have certain impurities that comes. For example, this is phosphorus and others are silicon. So by this you can easily identify whether it is a semiconductor or not. Regarding p-type, n-type, if it's a pentavalent, if it is doped with pentavalent impurities, like in this manner, then we call it as n-type. Pentavalent means the valency is 5. Or if it is trivalent, then we call it as p-type semiconductors. So this is the quick recap. This formula you have to remember. Ne means number density of electrons, number density of hole. Ni is the number density for intrinsic semiconductors. So Ne multiplied by Nh, this is equal to the Ni square. Means any number density of electrons, number density of holes, this is equal to square of intrinsic semiconductors. All right, so let's do some questions on it. Okay, let's discuss it. So see, Ni, this is given to you. Ni is what? Hole concentration. This is given to you what? 1.5 into 10 to the power 16. And see, what is NH given to you? Number of hole means hole concentration. So hole concentration is 4.5 into 10 to the power 22. See how we have done this. Ni means number density of intrinsic. In case of intrinsic, you have equal number of electrons and holes because no impurity is present. When do you have electrons and holes equal? So equal electron and hole is present in this only, this one. So that's why you have NH is equal to 4.5 into 10 to the power 22 and Ni is this. Now you just have to find Ne. So this relation Ne is equal to Ni square by this is NH. So Ne will be equal to Ni square will be 1.5 into 10 to the power 16 whole square divided by 4.5 into 10 to the power 22. So this will be 5 into 10 to the power 9 per millimeter. All right, just note it down and we'll do one more question. Okay, let's discuss it. See, you don't have any concept of semiconductors in this. Mainly, you have to use the energy formula that we have done in dual nature and modern physics. If the energy of a photon of sodium light is what? Wavelength is given to you. Wavelength is what? 589 nanometers. This is the wavelength given to you. All right. Now see, if this is the wavelength, then you have to calculate the energy. Energy will be equal to the energy gap, which is equal to hc by lambda. So hc is what? 6.6 into 10 to the power minus 34. This is your Planck's constant. C, speed of light, 3 into 10 to the power 8 meter per second, divided by the wavelength is 589 into 10 to the power minus 9 meters. This much of energy. So this will come out in joule. If you divide it by this whole term, 6.6 into 3 into 10 to the power minus 17 by this whole term, 589. If you divide this term by 1.6 into 10 to the power minus 19, you will get the answer in terms of electron volt. So this will be around 2.1 electron. All right, noted. Yes, Mariam, N type. But what's the reason for it being N type?
Because it is said that it is below the conduction band, so it has more holes.
More holes? Then it is a P type.
I mean, it has more
Electrons.
Yeah.
Electrons. See, excitation of electrons from the impurity level to the conduction band increases the electron density in the conduction band. So as the electrons are the majority carriers, so that's why the material is of N type. Calculate the wavelength also. What is the wavelength? The second part of the question. First part is correct. It is N type. Right.
I don't know the formula.
Formula we have just done the previous question.
Oh, okay.
You have the energy 30 milli electron volt wavelength. Not 6 point something. See, wavelength will be what? Maximum wavelength will be equal to hc divided by the energy. So hc is 6.6 into 10 to the power minus 34, the Planck's constant. And the speed of light is 3 into 10 to the power 8 meter per second. Energy is given to you as 30 milli. So convert milli into 10 to the power minus 3. Now electron volt also you need to convert. So this will be multiplied by 1.6 into 10 to the power minus 9. Now this unit is now in terms of meter. So maximum wavelength will be somewhat 4.125 into 10 to the power minus 5 meters. Okay, in this way. Just note down it, please.
Ma'am, why did we multiply with 1.6 into 10 to the power minus 19?
Because the energy is given to you, this is given to you as 30 milli electron volt. Now the SI unit of energy is joules, so we don't require this. So we have to convert this whole term into joule. So conversion of milli requires 10 to the power minus 3. Electron volt is converted by 1.6 into 10 to the power minus 9. This
Okay.
multiplication will give us joules. Okay, regarding PN junction, so PN junction, this is a single crystal dope with pentavalent, making it P type on one side and N type on other side. So this junction is known as PN junction. Now see, diffusion process occurs and drift occurs. These are the two contrary processes that occur. So in case of diffusion, flow of majority charge carriers occur. And then flow of majority charge carriers across the junction. That is known as flow of majority charge carriers across the junction. This is known as diffusion. In case of drift, due to electric field, minority charge carrier moves across the junction. So these two processes occur. One is diffusion, other one is drift. So see, in case of P type, what kind of charges move? In case of P type, holes will move in case of diffusion, and drift, electrons will move. In N-type conductor, in case of diffusion, electrons will move while holes will move in case of drift. Then we have two types of biasing, forward biasing and reverse biasing. If the P type is connected to the positive terminal of the battery and N type is connected to the negative terminal of the battery, we call it as forward biasing. So major characteristics of forward biasing include that majority charge carriers move, barrier potential decreases, width of depletion region also decreases, and the resistance of depletion region decreases. Then we have reverse biasing. In reverse biasing, P type is connected to the negative terminal of the battery, while the N type is connected to the positive terminal of the battery. So minority charge carriers flow occur in this case. So all the phenomena which were occurring in forward biasing gets reversed in this case of reverse biasing. It means the barrier potential now it will increase. Width of the depletion region will increase. The resistance will increase. Whereas all these quantities were decreasing in case of forward biasing. So you have to remember the differences. Theoretical questions will come on basis of this one. So the one which is at higher potential, you have to identify. Like, let me give you some questions. How to identify whether it is forward biasing or reverse biasing. See, the first part will be what? First part will be forward bias. This will be forward bias. Now see the reason. This is P type, this is N type. P type is connected to the voltage that is higher. So higher is connected with P, lower is connected with N. That is the setup for forward biasing. Then if you have, in this case, what is this symbol, Mariam?
Ma'am, which one?
This symbol.
Earthing?
Earthing, correct. So in case of earthing, your potential becomes zero. So now P type is connected to the one with lower and N type is connected with the higher voltage. So this is reverse biasing. Now here also V is 0. But see, this is not plus 10, this is minus 10. So P is connected with the lower one, N is connected with the higher one. So this is again reverse biasing. Whereas in case of third one, this P type is connected to minus 5 and N type is connected to minus 12. So minus 5 is greater than minus 12. So this is forward biasing. Forward biasing, why? Because P type is connected to the higher voltage and N type is connected to the lower voltage. Minus 5 will be greater than minus 12 anyways. So that's why. That's why this will be forward biasing. Just note it down.
Done, ma'am.
Done?
Yes.
Okay. Now see, one more question. Very short question. Yes, Mariam, bulb 1. So reason?
D2 is reverse biased and D1
D1
is
is
forward.
forward bias. Correct. Perfect. So that will be the answer. Now, see, so this is about PN junction. The last revision topic is rectifiers. Now, see, rectifiers, you have to remember that what is meant by a rectifier. So, rectification is actually the process of converting AC into DC. When AC is converted, this AC is converted into DC, direct current. Alternating current is converted into direct current. Then this process is called as rectification. And the device used for this rectification process this device is called as a rectifier. Now rectifier are of two types. One is the half wave rectifier, other one is the full wave rectifier. So example of rectifier is your mobile phone charger as well. Now see, in the difference between half wave rectifier and full wave rectifier, in case of half wave rectifier, you have a step down transformer. As in, you have a power supply where you have the input and then the whole setup of diode arrangement with a inductor connected to a diode connected to a resistor. The setup of a transformer, step down transformer, step up transformer and step down transformer. These transformers, I think you must have studied in alternating current already. So these are the setup for required for a half wave rectifier. Now see what happens whenever the waves are generated. Whenever these waves are generated, so only one diode is present. So if it is forward biased, then this wave signal will occur. When there is reverse biasing, means negative sign is coming over here with P. So in case of reverse biasing, the graph won't read any of the wave because no current will flow in case of reverse biasing. So there's a gap. Then again it will be forward biasing and the graph will come. So this is how the graph of a half wave rectifier looks. For AC it will be constant, but for DC it will be blocking DC. Now in case of full wave rectifier, you have such an arrangement. Again you have transformer setup only. So transformer setup is there with this center tap system. So D1 is one diode, D2 is another diode. So if one diode takes into account reverse biasing, other one takes into account the forward biasing. So whenever reverse biasing occurs in one, the forward biasing in other manages this gap. So now we do get this curve in case of full wave rectification. We don't get this in case of half wave rectification. The reason of it is that only because in case of half wave rectification, a single diode is there. So in case of reverse biasing, that gets omitted. Now in case of full wave rectifier, you have two diodes to manage. So the reverse biasing that was coming because of it now is not able to come. Why? Because you have the other diode, this D2. This D2 is there to just overcome this, means perform the function of forward biasing. Now see, apart from these diodes, we have special purposes diode, like the Zener diodes are there, like the photodiodes, we have light emitting diodes, we have solar cells. So Zener diode has been completely deleted from your syllabus. So you are not supposed to do Zener diode now. But regarding the other special purposes diode, you should be able to at least know some of the basics of them and should be able to know the graph of each one. Graph is essential because you might get the graph. Now see, in case of photodiodes are these transparent glasses with PN junction. So they are in reverse biasing and you should remember the graph in this manner. This is the intensity graph for it. In current versus voltage graph. So this gives different intensities. This is dark current, this is I1, this is I2. These are the different intensities. Yes?
The graph is in the negative axis?
Negative, third quadrant.
Okay.
And LED is light emitting diode. Now, in case of photodiode, that one is reverse biased. LED is forward biased. So you have to remember these materials, especially gallium arsenide. This comes in the examination, and most of the time it comes in the examination in the form of this only. Means instead of giving LED, it will give you draw the graph for gallium arsenide infrared. So you have to draw it in this manner. This is the parabolic graph of it. So in current and voltage are not directly dependent on each other. They are inversely proportional to each other. That's why we get such a graph. They are directly proportional, but in the power of 2, not single linear equation. Then we have solar cell. Solar cell converts the solar energy, means the energy of the sun, into electrical energy, which is electric energy, which you know. So you have two cases in the graph of it. One is this, where the current is 0. So if current is 0, then what will happen? If your current is 0, means your circuit is an open circuit, no current is flowing. And if there is excess of current, means potential is 0, then you say you have shorted the circuit. short circuit has occurred because lots of current has flown. So this is the graph for solar energy. You should remember that it is in the fourth quadrant. So this solar cell converts solar energy into chemical energy, means basically it absorbs photons, the H nu, light radiations, and then converts it into electrical energy for our use. So electrical energy can be utilized. So these are the special types of diodes that we have. So you should remember which type of biasing occurs, what is the setup of each of them, and the graph of each one. All right, is this clear?
Yes, ma'am.
Any doubt?